Hey, it's Professor Dave. I want to tell you about complex numbers.
He knows a lot about all kinds of stuff. Professor Dave explains.
We've pretty much wrapped up all the algebra we're going to cover in our study of mathematics, which means we need to move on to trigonometry and then the dreaded calculus. Before we get to those subjects, there are a handful of one-off topics that are important to understand, but didn't quite fit into the flow up until this point. So let's knock these out before moving on to harder maths. The first of these concepts is complex numbers. When we were discussing the types of numbers, we said that there are real numbers, which are all the rational and irrational numbers, like -5, or pi, or 7/3. But there are also imaginary numbers. These are the ones we get when we try to take the square root of a negative number. The simplest imaginary number is I, in lowercase italics, and it is equal to the square root of -1. We need this number because there is no real number that when squared gives -1, and that's why I is imaginary. But sometimes we can manipulate I to get real numbers. I squared, for example, is root -1 times root -1, which is -1. I cubed can be expressed as I squared times I, and we just said I squared is -1, so I cubed is equal to -I. I to the fourth is I squared times I squared, or -1 times -1, which is 1. This series of 4 values repeats every 4 powers of I, so I to the 5th through 8th will be these values once more, and then we start again. I can also be found with other numbers. Take the square root of -9, for example. This can be expressed as root 9 times -1, and therefore root 9 times root -1. Root 9 is 3, and root -1 is I, so we get 3i. In this way, the root of -x will always be I root x. Anytime we have imaginary numbers together with real numbers, they are called complex numbers, and we write them in the form of a plus bi. Complex numbers have a real part, that's the a, and then an imaginary part, which is bi. In this way, all numbers are technically complex numbers because if b is 0, the imaginary part goes away, and we just have a real number. If a is 0, we have a pure imaginary number, as there is nothing real about it. But if a and b are both non-zero, we have a complex number in its standard form. We can do operations with complex numbers just like we would if I was some variable, like x. If we had the quantity 2 plus x plus the quantity 3 minus 2x, we would add the numbers together to get 5, and add the x's together to get -x. It's exactly the same with I, so if we change these x's to i's, we get 5 minus I. Since we already know how to do this, we won't need to practice. Multiplication and division work the same way, with just one extra twist. We have to remember that I squared equals -1. So let's say we have the quantity 2 minus I times the quantity 4 plus 2i. We can just FOIL this exactly the way we would with two binomials. First gives 8, outer gives 4i, inner gives -4i, and last gives -2i squared. The two I terms cancel each other out, and -2i squared is -2 times -1, which is 2, so we get 8 plus 2, or 10. This is how complex numbers can sometimes multiply to give real numbers. This fact will come in handy if we want to divide complex numbers. Take something like 5 plus 2i over 3 minus I. Obviously, we can't do much with this as it is, but if we had a real number in the denominator, we could do something. As we just learned, it is possible to multiply complex numbers to get a real number, so we can multiply the top and bottom of this quotient by the same complex number to do exactly that. But what will this complex number be? As it turns out, We will always get a real number when we multiply a complex number by its complex conjugate. The complex conjugate of a complex number is just the same number but with the sign in between the two terms reversed. So in this case, we want to multiply the top and bottom by 3 plus I. If this had been a plus, we would use a minus instead. But now we can FOIL the bottom and the top. Let's do the top first. 15 plus 5i plus 6i plus 2i squared. We combine these to get 11i, 2i squared becomes negative 2, and we end up with 13 plus 11i. Then on the bottom, we get 9 plus 3i minus 3i minus I squared. We notice that the I terms cancel out, which was exactly the plan, and this will always be the case when we multiply complex conjugates. The negative I squared becomes positive 1, leaving us with 10. Then we can just express this in standard form by splitting it up into two fractions, 13 over 10 plus 11i over 10. And even though it's a little messy, that's the way we divide complex numbers. Where might we see complex numbers? Well, remember when we were finding solutions to polynomials, we would sometimes use the quadratic formula. But if the number under the radical, or the discriminant, turned out to be negative, we said that there were no solutions. Well, in truth, there were no real solutions. We can get imaginary roots if we express them in terms of I. For quadratics with no real solutions, there will be two solutions in the form of complex numbers, and they will specifically be complex conjugates. In this way, a polynomial of degree n will always have n linear factors. There can be repeats, so they aren't always all unique. They aren't always all real numbers either. Some could be pairs of complex conjugates, as we just saw with the quadratic. But if we take all of these into account, an nth degree polynomial will always have n linear factors. This truth is known as the linear factorization theorem. Complex numbers are very important in math, so let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.